The Common Type System, commonly known as CTS, is one of the most fundamental components of the .NET platform. It defines how data types are declared, used, stored, and managed at runtime. In a multi-language environment like .NET, where different programming languages such as C#, VB.NET, and F# coexist, a unified type system is absolutely necessary. CTS provides this uniformity by defining a common set of rules that all .NET languages must follow. Without CTS, it would be impossible for different languages to interact with each other reliably within the same runtime. The main goal of CTS is to ensure language interoperability. When an object is created in one .NET language, it must be usable by another language without confusion or data mismatch. CTS guarantees that every type, regardless of the language in which it was written, follows the same internal representation. This common understanding allows seamless communication between components written in different languages. Before the introduction of .NET, language interoperability was extremely difficult. Each programming language had its own type system, memory representation, and calling conventions. Combining components written in different languages required complex wrappers or interfaces. CTS solves this problem by defining a single unified type system that all languages compile into. When a developer writes code in a .NET language, the compiler does not generate machine-specific instructions directly. Instead, it converts the source code into intermediate language, IL, along with metadata. This metadata contains detailed information about types, including their structure, visibility, members, and relationships. CTS governs how this metadata is created and interpreted by the Common Language Runtime. The CTS defines two broad categories of types: value types and reference types. These two categories form the foundation of memory management and behavior in .NET. Understanding this distinction is critical for understanding how applications perform and behave at runtime. Value types are types that store their data directly. When a value type is assigned to another variable, a copy of the data is created. Examples of value types include primitive types such as integers, floating point numbers, booleans, characters, as well as structures and enumerations. Value types are typically stored on the stack or inline within objects. Because they are copied by value, they are generally faster and more memory efficient for small data. Reference types, on the other hand, store a reference to the actual data rather than the data itself. When a reference type variable is assigned to another variable, both variables point to the same memory location. Classes, arrays, delegates, and interfaces are reference types. Reference types are stored on the managed heap, and their lifetime is managed by the garbage collector. This clear separation between value and reference types is one of the most important features defined by CTS. It ensures predictable memory behavior and consistent semantics across all .NET languages. CTS also defines how types relate to one another. It supports inheritance, polymorphism, and interface implementation. All types in .NET ultimately derive from a single base type, System.Object. This is a core rule enforced by CTS. Because of this, every type in .NET inherits common methods such as toString, equals, getHashCode, and getType. This universal inheritance simplifies runtime behavior and enables consistent object handling. By defining System.Object as the root of all types, CTS ensures uniformity. Whether a type is a value type or reference type, it can be treated as an object. This concept enables boxing and unboxing, where value types can be converted into reference types and vice versa. Although boxing involves performance overhead, it provides flexibility and interoperability. CTS also defines accessibility rules. It specifies how types and their members can be accessed using modifiers such as public, private, protected, and internal. These rules ensure consistent access behavior across languages. For example, a public method in C# is guaranteed to be accessible from VB.NET because CTS defines the meaning of public in a language-neutral way. Another critical aspect of CTS is type safety. Type safety means that operations are performed only on compatible data types. CTS enforces strong typing at runtime, ensuring that an object cannot be treated as a different type unless explicitly allowed. This prevents memory corruption and illegal operations, making .NET applications more stable and secure. Type safety also plays a major role in runtime verification. Before executing IL code, the CLR verifies that it adheres to CTS rules. This verification ensures that code does not access memory outside its bounds or misuse object references. This is a key reason why managed applications rarely crash the operating system. CTS also defines how methods are called and how parameters are passed. It specifies calling conventions, return types, and parameter types in a standardized manner. This ensures that methods written in one language can be invoked from another language without ambiguity. In addition to basic data types, CTS supports complex types such as arrays, pointers, and generic types. Arrays in CTS are objects with defined bounds and type information. This ensures array safety by preventing invalid indexing. Unlike unmanaged languages, .NET arrays perform bounds checking, which improves reliability. Generic types are another important feature governed by CTS. Generics allow developers to define type-safe data structures without sacrificing performance. CTS ensures that generic types behave consistently across languages and are enforced at runtime. This eliminates many runtime casting errors and improves code maintainability. CTS also defines how enums are represented. Enumerations are strongly typed value types that improve readability and safety. CTS ensures that enums have a defined underlying numeric type and consistent behavior across languages. Structures are value types defined by CTS that allow grouping related data without heap allocation. They are useful for performance-critical scenarios and are treated consistently across all .NET languages. Delegates are also defined by CTS. A delegate represents a type-safe function pointer. CTS ensures that delegates have a defined signature and invocation model. This enables event handling and callback mechanisms in a language-independent way. Interfaces are another important CTS feature. They define contracts without implementation. CTS ensures that interface definitions are consistent and enforceable across languages. A class written in C# can implement an interface defined in VB.NET without any compatibility issues. CTS also defines how types are named and identified. Each type has a fully qualified name that includes its namespace and assembly. This prevents naming conflicts and ensures uniqueness. The runtime uses this information to resolve types accurately during execution. The role of metadata is tightly coupled with CTS. Metadata describes every type defined in an assembly, including fields, methods, properties, and attributes. CTS rules determine how this metadata is structured. The CLR relies heavily on metadata to enforce type safety, perform reflection, and manage execution. Reflection is possible because CTS ensures consistent type information. At runtime, applications can inspect types, discover members, and invoke methods dynamically. This capability is widely used in frameworks, dependency injection containers, and serialization libraries. CTS also supports versioning. Because type definitions are stored in metadata, different versions of assemblies can coexist without conflict. This helps avoid the DLL hell problem that existed before .NET. One of the major advantages of CTS is cross-language inheritance. A class written in one language can inherit from a class written in another language. This would be nearly impossible without a common type system. CTS ensures that inheritance hierarchies are respected regardless of language boundaries. Another important benefit of CTS is consistent error handling. Since exceptions are also types derived from System.Exception, they follow CTS rules. This ensures that exceptions thrown in one language can be caught and handled in another language without any mismatch. CTS plays a vital role in memory layout. It defines how fields are arranged in memory and how objects are represented internally. This consistency allows the garbage collector and runtime services to work efficiently. CTS also supports attributes, which provide declarative information about types and members. Attributes are stored in metadata and interpreted by the runtime or frameworks. CTS defines how attributes are applied and accessed. From a developer perspective, CTS is mostly invisible. Developers rarely interact with CTS directly. However, every line of .NET code depends on CTS rules. Without CTS, features like inheritance, polymorphism, reflection, and interoperability would not function reliably. In enterprise systems, CTS ensures that components built by different teams, using different languages, can integrate smoothly. This makes .NET a powerful platform for large-scale application development. The relationship between CTS and CLS is important to understand. CTS defines all possible types and behaviors, while CLS defines a subset of CTS that languages must support for interoperability. A language may support more features than CLS allows, but only CLS-compliant features are guaranteed to work across all languages. CTS is broader and more powerful than CLS. It provides the complete definition of the .NET type system, while CLS focuses on compatibility rules.
In moderne.NET développement, CTS remet un fondational concept.
Even though most developers use C#, the runtime still relies on CTS to ensure consistency and correctness. Whether running on Windows, Linux, or cloud platforms, CTS continues to provide a unified type model. In conclusion, the common type system is the backbone of the .NET runtime type architecture. It defines how types are created, stored, accessed, and executed. It ensures language interoperability, type safety, memory consistency, and runtime reliability. By providing a unified type system, CTS enables multiple languages to work together seamlessly within the same runtime. Understanding CTS gives developers deep insight into how .NET works internally and forms a strong foundation for mastering CLR architecture and advanced .NET concepts.